Hi guys, this is Mr. Morris. We are starting our unit on electricity, or continuing with what you started the other day. I'm going to talk mostly today about static electricity and where electric charges come from. And then later we'll get into electrical forces and then into electrical circuits, how light bulbs work and how we produce electricity and things like that. So lots of good things coming up. Um, First of all, electricity starts with things that you already know about, the atom. So we need to make sure we know all of our parts of the atom. You've had this in physical science and probably in chemistry, if most of you have taken chemistry by now. So protons are our positively charged particles, electrons the negatively charged particles, and neutrons, of course, have no charge. Remember that the neutrons and protons make up the nucleus, and then the electrons are much smaller relatively compared to protons and neutrons. They have almost no mass. They're thousands of times smaller. So we consider them massless in the atom, even though they're not, of course. But when we talk about the makeup of the atom's total mass, we add up the mass of the electrons and neutrons. The mass of an electron and neutron are relatively the same, but charge-wise, even though a proton is thousands of times smaller than an electron, electron is thousands of times smaller than a proton, their charges are about the same. So one electron can neutralize the charge of one proton, and vice versa. Remember, the electrons are held in the outside of the atom, in the orbits around the atom, and the protons and neutrons are in the nucleus. And when atoms become charged, so when something becomes negatively or positively charged, it's not because the protons leave or are added to an atom. It's because electrons are added or leave the orbits of the atom. Okay, so ions are things that are charged. When we have a positive charged ion, it's because we are missing electrons or there's a deficit of electrons. And we have a positive or negative charged ion, it's because we have an excess in electrons. We know that oppositely charged objects attract. So there's an electrostatic force between any charged objects such that positive charges will attract negative charges, and negative charges are attracted to positive charged objects. Likewise, positives and positives repel, and negatives repel. Okay, so like charges repel and opposites attract when we talk about electrically charged objects. Okay, so to sum that up, here it is: charged objects repel. Positively charged objects repel positively charged objects. Negative charged objects repel negatives. The question is, though, then charged objects and uncharged objects, neutral objects. So neutral objects will also be attracted by positively charged objects, and neutrally charged objects will likewise be attracted by negatively charged objects. And the question is why? So here in this diagram, what we're talking about is what's called inducing a charge in an object. So I've got something that's negatively charged. In this case, it's a rubber balloon. So you guys have probably seen this before. We're going to take a rubber balloon, rub it on some fur, or rub it on your hair even, and you've probably stuck the balloon to the wall. And if you haven't done that, then you should try it. Get yourself a balloon, blow it up, rub it on your hair, and then it will stick to the wall. And the question is, why would it stick to the wall? But here's a little bit of reason why. If I hold that thing close to the soda can, I'm not going to touch it, but I'm holding it close to it. What happens is that the electrons in the soda can are repelled by the negative charge of the rubber balloon. So since the rubber balloon has excess electrons, when I rub the rubber balloon onto my hair, the balloon picks up electrons from my hair, and now it is negatively charged. So when I hold it next to the soda can, electrons move from the left to the right, and then the soda can becomes what's called polarized. It's not charged. It still has the same amount of positive charge and negative charge in it. But you can see in the third picture over here that the negative charge has moved as far to the right as possible, trying to get away from the negative charge of the rubber balloon. So since the electrons can move and they're repelled, they move as far away as possible to the other side of the can. Okay. In this diagram here, it shows that the setup that would occur then. So the electrons move far to the right to get as far away from the negative charge in the rod. We're not touching it, okay, but we're bringing it really close. The same thing would happen if we bring a positively charged rod close. The electrons would be pulled toward the left-hand side of the surface of the sphere and leaving the right-hand side positively charged and left-hand side negatively charged. When we talk about a charge, here's the definition. A charge is a buildup of electrons. It's measured in coulombs, and the symbol is Q. The electrons, remember, move in random paths around the nucleus at high speeds. You should pause here if you need to write this down. Now, you learn in chemistry that electrons in metals are held fairly loosely. In other words, we talked about the octet rule, and we have lots of atoms that have 7 or 1 electrons, and some of them are very good acceptors of electrons but don't give up electrons, and vice versa. Metals typically have 3, 4, 5 electrons in the outer shell, and therefore they're able to give up and accept electrons fairly readily. Likewise, metals can carry lots of extra electrons, so they make good conductors. And there are places where electrons can build up on the surface. But any object can likewise build up a surface charge. Like we showed in the previous example, a rubber balloon built up a surface charge of electrons. And there are different objects that have different affinities for electrons, and we'll talk about those in a different slide. But that explains why when I rub the rubber balloon on hair, that electrons leave the hair and go to the rubber balloon instead of leaving the rubber balloon and going onto the hair. It's dependent upon the affinity, is what we call that, for the electrical charge. When a large number of electrons build up on a surface of an object, it's called a charge. So the buildup of the electrons is called a charge. The object would then be called a charged object. And this is what we call static electricity. Static from Latin means not moving. So we have static electricity, meaning we have a buildup of electrons, but they're not at this point moving anywhere. We represent charge. I'm not recording, are we? Sorry about that. We represent charge by indicating positives or negatives. The little u here stands for micro. So most of the time when we have a charged object, we don't have a full coulomb of charge on the object. So this refers to as microcoulombs. Micro is similar to when we do centimeters or millimeters. Micro would be times 10 to the 6th, or negative 6, excuse me. So it's very small. So we're talking about a positive microcoulomb of charge here and negative coulombs of microcoulombs of charge here. But notice this one would be positive 7 microcoulombs and this one negative 3. A coulomb of charge is actually thousands and thousands of electrons. So we talk about electrons moving from one surface to another. It's literally thousands and millions of charges that move when we make up a coulomb of charge. In this case, since these are positively and negatively charged, what will happen is that when we touch them together, that some of the charge from one will move to the other and vice versa. Okay? And we call this total or conservation of charge. And what conservation of charge is, you've had a few conservations like conservation of energy and conservation of momentum. Conservation of charge means that whatever the total charge is in the system, and our system right now is just these two objects, whatever the total charge in that system is that the total charge remains the same. And if you look, my total charge between positive 7 and negative 3 should be positive 4. Okay? So we never lose charge. And when we touch these two things together, when we touch those two things together, we would have a charge of positive 4, and it would be equally distributed with positive 2 on this sphere and positive 2 on this sphere. I had a slide that showed that, but it doesn't seem to be popping up, so I apologize. Okay, there are 3 ways to charge objects. The first is by friction, and that's when we just rub two materials together. And I talked about that with the balloon and the hair. And so if we rub the balloon on the hair will give up electrons onto the balloon. The balloon essentially becomes negatively charged, and the hair would become positively charged in that situation. When we do this, electrons transfer from one object to the other, and they'll be stored. When this occurs, we know that the amount of charge in the negatively charged object and the amount of charge in the positively charged object are the same. In other words, if one receives a charge of, let's say, positive 2 coulombs, then the other becomes negatively charged with negative 2 coulombs. And it's because the amount of charge leaving becomes the excess on the one object, and the amount of charge leaving becomes what's missing on the other one. Okay, so if I take 2 away from one, it becomes positive 2 on the one and negative 2 on the other. Again, this is just a restatement of conservation of charge. And here's a great example of this. You guys have probably seen that with the small child sliding down the plastic sliding board, and the plastic does a great job of picking up electrons, and the body and the person, the hair and the clothes lose electrons um, in that case and becoming charged. So here you can see a list of different objects. You might want to take a picture of this or jot it down. Maybe just give some examples or just pay attention to some of them. But for example, when we rub the human hair, let's see right here, human hair rubbed against the rubber balloon. I don't have the balloon, but we do have a rubber object here. Okay, notice that the arrow for the electrons shows that the objects down here are going to be great electron acceptors, and the ones up here are going to be good at giving up electrons. Okay, so similar here, we look at the child sliding down the sliding board, and the sliding board is made of a plastic, probably PVC. Okay, so we've got the PVC or some other type of a plastic object here. And you see PVC, polyethylene, cling film, all of these things are types of plastic are down here. Up here are human skin, human hair, things like nylon, wool, silk, different types of clothing fiber that are up here. Even cotton is kind of toward the top of the list there compared to the PVC and polyester and other, or polyethylene and things that are down this way. So we can see that the plastic of the slide would be a good electron acceptor, and that the little girl, being human with human skin, human hair, and wearing clothing, is going to be a good electron donator. So the girl is becoming very positively charged, and the tube is becoming very negatively charged. So now that she's positively charged, her hair is being attracted and pulled toward that plastic slide with some pretty good force, as you can see. Okay, so you don't have to have this list memorized, but it's good to know. So when we charge by conduction or contact, what we have to do is, first of all, touch the two objects together, and the electrons transfer. So that we talked about conduction, and we're going to talk about induction. Okay, when we charge an object by conduction, we have to touch the objects. Okay, when we talk about induction, we will not be charging the objects. Okay, electrons transfer as soon as there's contact. So this is similar to what you experience with static cling or static charges in. Sorry about this silly slide, but there's going to be a charge. Anyway, let's say it's a winter day and you rub your feet across the carpet and you build up a charge on your body, and then you go touch a doorknob, and what happens is that you are charging the doorknob now by conduction. Okay, so you have a buildup of electrons on you, you touch the doorknob, and it transfers electrons to the doorknob from you. The doorknob likewise becomes negatively charged now. You and the doorknob are still negatively charged and have some type of a balance in charge at that point. But some of the electrons move from you into the doorknob until they're relatively equal in charge. And that's charging by contact or conduction. Now when this happens, the two objects are not necessarily charged equally. Okay, so for example, my example of the static charge. So I build up electrons on me and I touch the doorknob. Okay, I do not have the exact same affinity for electrons as the doorknob. As we discussed in the previous slide, certain things accept electrons better than others. So although some charge will move, probably more moves off of me and onto the doorknob than stays, because the doorknob itself, being a metal, will accept electrons better than my body will. Okay, so it's probably better to store electrons there, and we will not have equal charge in that case. But if we have two objects made of the same material, we will have an equal charge. So for example, one metal sphere has a charge of -4 microcoulombs, and another identical sphere has a charge of +10 microcoulombs. They are touched together and then separated, and we want to know what's the charge on each. Okay, so since we have a -4 and a +10, we have a total charge of +6. So after I touch these two things together, the electrons will redistribute, and we will have a net charge of +6 still, with one sphere having a charge of +3 and the other sphere having a charge of +3 as well. The two major things to keep in mind when we're doing charge by conduction and charge by contact is that, number one, the charged object that I'm going to touch to it, the charge on the new object, it becomes the same as the charge on the old object. For example, I'm going to have a positively charged rod. I'm going to touch it onto a neutrally charged ball, and the ball becomes positively charged. So I'm using a positively charged rod to transfer positive charge onto the other object. The second thing is that there has to be contact, that you're actually going to touch those two things together. Now, when we charge by induction, when we're charging by induction, we don't actually touch the charged object. Okay, so two differences here. Number one, we are not going to touch the object. We're going to polarize the object, just like we talked about before, meaning we're going to force charges in the new object to move to one side or the other. But we're not actually going to touch it. The second thing to keep in mind is that we're going to charge the object opposite the charge of the rod. Okay, so in the previous example, if I would take this negatively charged rod and I were to touch it onto this neutral object, some of the electrons would flow off of it and it would become negatively charged as well. But when I bring it close to the other object, it forces the electrons in this object to move as far to the right as possible. As far to the right as possible. Now, if I were to touch my finger or a wire over here, it would give the surface, it would give the electrons a path where they could get even farther from this charged rod. So in picture B, the electrons have moved to the other side of the sphere, and they're as far away from this charged rod as possible because they're repelled. But if I give them another option, if I give them a wire, let's say, that's connected to the Earth or connected to me, the electrons can now get even farther away from the sphere. Okay? And they're now onto that wire or onto me or into the ground. And we call that a ground whether it's touching the ground or not. Okay, I can call my finger a ground if I want to touch the side of this sphere. What a ground does is it gives another large object, we call it kind of an electron sink. Okay, it acts as an electron sink or an electron source where you can dump lots of excess electrons or you can pull off a lot of excess electrons. And the Earth makes a great ground, and we use that in our houses to ground electrical appliances and things. So every home has a large copper or steel wire that leaves the home and goes into the earth outside of the house. Every single home does if you have electrical power in your house. So now these electrons can get even farther off of the sphere. And then when I disconnect the wire, they can't get back on. Okay, and when I pull the rod away, this is left with a negative charge. And they're symbolizing it, it looks like with 8 positive charge and 8 negative charges in this sphere. We're forcing them to the right. 4 of them end up leaving, and we're left with 4 that are still pushed to the other side. And when I move the rod, they rearrange and go back to normal positioning. But notice that this thing is now positively charged because some of the electrons have been forced off the other side by the negatively charged rod. So again, with charging by induction, we're not going to touch the charged object to the neutral object. We're going to bring it close, and then we're going to provide a path to force charges to leave, to force electrons to leave. In the same way, if this rod were positively charged, we would pull the electrons toward it, we could connect the ground, and we could pull new electrons onto the surface toward the object because the right side of the object would be positively charged. So using a positive rod, I can put a wire here and draw electrons up, and by using a negative charge rod, I can put a wire here and push electrons down. Again, charging by induction, we provide a ground, so that provides a path for electrons to go. As I mentioned, if you look outside your home, you may see something like this. Okay, probably close to where your electrical box comes into your home, you will see a nice shiny copper wire that is connected to a post that goes into the ground. This would be an example of where the wire is attached to a water pipe in the basement or something like that. It's usually connected to a cold water pipe, and the water pipe then runs outside. But so many homes have plastic plumbing anymore that things are grounded individually in the house with wires. We used to ground everything onto the plumbing, and now instead we use wires because so much of the plumbing in homes is plastic now. We said that polarization is charge separation. We're going to bring an object close but not touch so that the opposite charges are repelled as far as possible. And then we provide a path for them to leave, such as touching with my finger. And now this ball would be left positively charged. Lightning is a great example of separation of charge. Okay, so what happens with lightning? What happens with lightning is that charge separation happens inside of a cloud. Now, we're not fully aware of why charge separation happens in the cloud, but it does. And we end up with certain areas of cloud that are very positively charged and certain areas of cloud that are very negatively charged. Notice here in this diagram, the negatively charged bottom of the cloud forces electrons on the Earth to go deeper into the Earth, leaving the surface of the Earth more positively charged. Okay? The same thing's true with the picture of this woman over here and her hair standing up. Okay? We have a very negatively charged object close to her, and so her hair stands up. Electrons are pushed down toward her feet, and her hair is pulled toward the negatively charged object because her hair becomes positively charged. So here the surface of our Earth becomes positively charged. And at some point, if that charge separation becomes strong enough, what we have is a difference of charge and we have a force. Remember that positives attract negatives. Well, if they're attracted enough and there's enough of a buildup of them, they can actually gap through the middle of the air. You don't have to touch. So my example of me touching the doorknob, when I touch the doorknob, I actually have to make contact with it so that the charge leaves me and goes to the doorknob. But perhaps you've seen sometimes when you have a big charge, right before you touch the doorknob, the electrons jump off of you and onto the doorknob, and there's a little bit of spark that goes through the air. That's a tiny little lightning bolt. And as long as this buildup is really huge and the removal of charge down here is really huge, we can get those things to jump huge distances, as you see in this picture over here, of course. So you've seen lightning bolts that cover gaps of thousands of feet as they jump from a cloud to a building or to a tree or to some other surface. And that occurs when we have huge buildups of charge, okay, very large amounts, and that electrical attractive force between these two surfaces becomes so great that we can have what's called gapping or arcing. Okay, and when arcing occurs, it's actually the jump of electrons through air without actually traveling along a conductor or a wire. Okay, we said that conductors are things that allow electrons to flow through them, such as metals. Metals make good conductors. And insulators are materials that do not conduct electricity very well, such as rubber, plastic, wood, things like that. Most objects fall somewhere in between being conductors and insulators. And it depends on the thickness of the material and things like that, and how much charge you're trying to push through it. At very, very, very high voltages, we can get electricity to pass through certain objects or pass between, or not through as a conductor, but a very high voltage wire that's wrapped in a real thin amount of rubber or something is not going to be real protective sometimes. We can get that charge to pass through if there's ample force. And so we said that good conductors are things like metals, and that atoms, obviously are more stable with 8 electrons in their outer shells. Learned that from our chemistry. And most of our metal atoms have 3, 4, or 5 electrons in outer shells. So they're readily available to accept or give up electrons. Like I said, most our best conductors are, for some reason, are hard to find or are high-valued metals. Things like gold, silver, and platinum make outstanding conductors. Copper is a fairly expensive metal and makes a great conductor as well. So not sure why the rare metals are the best conductors. The ones that are best conductors aren't found abundantly in Earth, but they're just not. So, but you'll find that certain electronics have gold-tipped or gold contacts between surfaces. A lot of computers will have gold-tipped conductors between the keyboards and in the processors and things like that, because they do conduct electrons a little bit faster than other materials. They even used to make gold-tipped spark plug cables for cars that people thought would give better contact and things like that. I'm not sure they work much better, but they definitely made them. I don't know if they still do, but back in the early and late 80s, I know you could get gold-tipped spark plug contacts for your car. So. Okay, well, we're going to stop our discussion there for today and pick up more on electricity and electrical charges at a later time. Thank you.